Time for some e-learning with Miss Atkin. E-learning with Miss Atkin. E-learning with the puppy. E-learning with Miss Atkin. Yeah. What's up, scholars? Today we're continuing our investigation of circles, and we're going to talk about arcs and chords. Now, we talked about some chords last time, where those were segments that intersect the circle. So adding to that, we're talking about arcs. And arcs are going to look like kind of what you think they would. Like, a rainbow's got an arc. It's going to be that shape. So it's going to be a chunk of the circle on the outside. So we've got this circle P. It's called circle P because it's centered at P. And let's make an angle off of that center. And we'll say the intersection with the circle is A and B. So since we made an angle that's based off of the center, this is called a central angle. Central angle, where the vertex is the center. Now we also chopped this circle up into two arcs when we did this. We have a minor arc and a major arc. So the minor arc, some colors going on here. There's our minor arc. It's minor because it's smaller, and any minor arc is less than 180. We have our minor arc, which is AB, and has this arc symbol on top. And minor arcs will always be less than 180 degrees. And then on the other side, we've got another arc here. But we can't call it AB because that was already the minor arc. Sorry, we have a major arc on the other side. We can't call it AB because AB is already the name of the minor arc. So let's put another point on the circle. And we'll call our major arc this guy on the outside. So it'll be called A. C, B, A, C, B, and our major arcs will always be greater than 180 degrees. Cool. Minor arc, major arc, central angle. Now there's another really special major arc that has endpoints on the diameter of the circle. So let's continue this line, this radius, through here. Call that point D. So our semicircle is going to be the arc here that has endpoints on the diameter dB. Semicircle, so that arc would be DCC. I guess I really misspoke because the major arc should be greater than or equal to 180 degrees. Greater than or equal to 180 degrees because the semicircle is technically a major arc as well. So I talked about these measurements here, but how do we actually measure an arc? Well, a minor arc's measure is going to be equal to the central angle. Equal to the measure of the central angle. Central angle. The major arc is going to be 360 degrees minus that central angle, because a whole circle is 360 degrees. So a major arc equals 360 minus the measure of the central angle. Keep running off my page here. Sorry about that. And then a semicircle is exactly 180 degrees. Okay, so let's do some examples finding some measures of some arcs. Okay, so for your example, let's draw a circle. Let's name that circle A. Let's draw a diameter through A and call its endpoints D and B. And then let's make an angle off of A here. Call that endpoint C, and we'll say this central angle is 148 degrees. Let's find the measure of minor arc DC. Well, that's just equal to the angle that it sweeps, so that's 148 degrees. How about the measure of arc BC? What's that guy going to be? Well, we made DB as a diameter, so it's going to split the circle in half. So this whole thing would be 180 degrees. So 180 minus 148 there. 180 minus 148 is going to get us 32 degrees. Now, how about what would be the measure of this large arc BDC? BDC. Well, we know that one's 32 now. So we can say 360 minus that 32. 360, because that's the whole circle, minus that chunk is our arc BDC. 360 minus 32 is 328 degrees. Let's line up the page there. Sorry about that. Cool. All right. Now, just like we had way back when, an angle addition postulate and a segment addition postulate, that's all I can think of right now. We're going to have an arc addition postulate, which says we can add the measures of two arcs together to get a third larger arc. There you go. There's our arc addition postulate. The measure of this major arc ABC is equal to the measure of AB plus BC. Easy peasy, lemon squeezy. So let's do an example with that guy. So here's our next example. We've got a circle, circle A. We've got a couple central angles based off of a circle A. Now we're going to find three different arc measures here. So if we want measure of arc BD, from B to D, that spans this central angle and this central angle. So let's add those two together. 60 plus 82 should be $142, I think. Great. 142 degrees. How about BE? Well, there's a couple of ways we could do this. We could take 360. Actually, let's just do that. We'll take 360, which would be the whole circle, and subtract off these three parts that we know. So we'll do 360 minus 60 minus 82 minus 100, and we shall get yes, 118 degrees. Fabulous. And how about the measure of arc Deb? Well, we said this one was here. This central angle is 118 degrees. So Deb, D to E to B, is going to be 100 plus 118. Sweet. Nicely done, scholars. Bunch of geniuses over here. Bunch of geniuses. A quick note about congruent arcs. They must have the same measure and be from congruent circles. So quickly, for example, if I had concentric circles here, where they share a center, and I drew a central angle off of both. So both of these arcs would have the same angle measure because they both sweep out the same angle in a circle. That circle's so lumpy. However, this arc here is clearly longer. So these are not congruent arcs. Not congruent arcs. Not ACRs, arcs. They're not congruent arcs because these circles are not congruent. Cool. All right, now let's talk about a bunch of chord theorems. Okay, our first theorem, theorem 10.4. In the same circle or congruent circles, two minor arcs are congruent if and only if their corresponding chords are congruent. So in this picture, this kind of looks like the Star Trek thing. I've been watching a lot of Star Trek Discovery right now, which is cool. So arc AB and arc BC would be congruent if chord AB and chord BC are congruent. Pretty cool. So that has nothing to do with the central angles they're sweeping out. It does really, but we don't need that in this case. We're saying if we know that AB is congruent to BC, then the arcs AB and arc BC will be congruent. Sweet. How about theorem 10.5 says if a diameter of a circle is perpendicular to a chord, so there's our diameter, it's perpendicular to this chord here, DF, then the diameter bisects the chord and its arc. What does that mean? That means the diameter splits this chord DF perfectly in half so that DE equals EF. And these little chords here are going to be congruent to each other. DG will be congruent to GF. Cool. So if a diameter is perpendicular to a chord, that chord gets split perfectly in half, so those sides are congruent, and these arcs are congruent. Great. And theorem 10.6, if one chord is a perpendicular bisector, meaning it's perpendicular to it and it splits perfectly in half, then that first chord must be a diameter. So that is the converse of theorem 10.5. If some chord is perpendicular and it bisects another chord, then that first chord must be a diameter. Cool. All right, let's do a couple examples using those theorems. So here's our example. We've got circle with center A. It's got two chords, DB and BC, that are congruent to each other. We are asked to find the measure of arc BC. So we can use that theorem 10.4 that said since these chords are congruent, since DB is congruent to BC, then the arcs are going to be congruent. Arc DB will be congruent to arc BC, which means these measures are equal to each other. So we can set those equal to each other. That 3x plus 11 is going to equal 2x plus 48. Little solvey, mathy. Minus 2x on both sides. X plus 11 equals 48 minus 11 minus 11. X equals 37. Finding measure of BC, we got to plug that back in. So 2 times 37 plus 48 is going to equal 2 times 37, 74 plus 48, 122 degrees. 122 degrees. All right, scholars, you're doing great. We have one more chord theorem we're going to talk about. That is theorem 10.7, which says in the same circle or congruent circles, two chords are congruent if and only if they are equidistant from the center. What? Well, that means here are chords CD and AB. If they are equidistant from the center is E, so the distance from E to G is the same as the distance from E to F. We know that because it's got those congruent marks, so they're the same length, but it's a distance, so it needs to be perpendicular to that chord. Right? So that length is the same because of that congruent mark, and then it's truly a distance because it's perpendicular. So, since this is true, then these chords CD and AB are congruent to each other. All right, let's do some examples with that, and that'll be all she wrote. It's going to be our last example because it's a good one. So we've got the circle, center at C. It's got chords AD and BE. It's got these segments CF and CG that are perpendicular to the chords. And then we've got, looks like a radius C to D. And we are tasked with finding the length of the segment from C to G. Okay, we're given some stuff, of course. It says AD is 40. So from A to D is 40. That's going to be the same thing over here. Right. Well, if AD is 40, and each of these chunks are equal to each other because they have those congruent marks, that means all of these guys are 20. Right? 20, 20, 20, 20. And we know that CD is 25. And since we know these chords are congruent and perpendicular to these segments here, using that last theorem we just talked about, we know these segments are congruent. Okay, what else do we see in here? Oh, I see a triangle. Oh, I see a right triangle. That's a right angle. This must be a right angle. So then I can use the Pythagorean theorem. Right? Yeah. This is our hypotenuse to our right triangle. So we'll say a squared plus b squared equals c squared. We'll make sure to plug in 25 for the c. Okay, so we've got a side that's 20 units long, plus some side I don't know. Call that x. We know 20 squared is 400. X squared is x squared. 25 squared is... What is 25 squared? I think it's 525. 625. There we go. 625. Subtract 400 on both sides. X squared is 225. Square root both sides. X equals 15. And we know that length is the same as CG, so it is 15 as well. Very cool. Very, very cool. All right, scholars, that concludes our section about arcs and chords. I love you. I will see you next time. Peace out.